Hello and welcome to the first video of the AQA revision. Okay, this is the first Hillyfields video for AQA revision S1. Today we're going to be concentrating on the binomial distribution. My name is Mr. Gibb.
And I'm Mr. Rashid.
And the whole purpose of this is an extended exam question which will help you with your revision and really cover most of the skills needed for your upcoming assessment.
Now it's very important after you've looked at this video that you go away and try some exam questions yourself, and there will be some links at the bottom of the video that you can use to get some exam questions.
So before we start talking about the binomial distribution, we need to think about what the conditions are for the binomial distribution.
So what are they?
First of all, you have two outcomes.
Now what if I roll a die? If I roll a die, I've got the numbers 1 to 6, can I use the binomial distribution?
You can, because you wouldn't look at whether 1 to 6 happens, you'd look whether 1 happens or 1 doesn't happen. So the outcomes would be 1 happens or 2 to 6 happens. That would be the binomial distribution. Either 1 happens or 2 to 6 happens. Likewise, if it's odd and even numbers 1 to 3, numbers greater than 3.
Cool.
There's also a set number of trials of the binomial distribution. Notation for which is n equals, and I'll have a fixed amount. The probabilities remain constant throughout that fixed amount. So if there are, for example, 100 trials, the probability would be exactly the same for the first trial all the way up to 100.
It's very important when you do this that you show the examiner that you know it's a binomial distribution question. So you need to write down this. Now it's not x is your variable, this b shows that it's binomial, and n here is your number of trials and p is your probability.
This is just an acknowledgement by you to the examiner that you know it's binomial, and this is how you're showing it to be binomial. Very, very important to do. So here's a real-life example, or real-world example for conditions of a binomial distribution model. So a new skin cream is launched. The producers say it has a 90% cure for acne. For a random sample of size n people that is assumed to be binomially distributed, state any assumptions made. Those assumptions are...
Okay, so looking at the question, it has a 90% chance of curing acne, so there's a 10% chance of not curing acne, and there we have two outcomes, curing or not curing. Okay. Now, it also says there's a random sample of n people, so we know there are a set number of trials. It's not infinite, there's a finite number of trials. The assumptions we need to make are that this probability is constant, that is always 90%, 0.9, and that the uses of the cream are independent from use to use.
So let's look at our first question. We have Mo, Joe, and Flo. Nice names. They're a sales assistants in a mobile phone shop. When a new customer enters the shop, the probability that Joe will greet them first is 0.35. Mo, greeting them first, will be 0.4. And Flo, a quarter. Oh, what's happening there? A quarter?
Well, a quarter is just another number. We know we can represent probabilities as percentages, decimals, or fractions. If you're not comfortable with a quarter, just write it as 0.25.
Okay, it's probably worth to add that these probabilities are independent, one of the conditions for the binomial distribution. 10 customers entered the shop on Monday. Find the probability that Mo was first to greet exactly 3 of the customers. Now, we have the probability for Mo, and we have a number 10. What does 10 represent?
Well, I think that it'll represent n, but why, sir?
N as in the number of trials?
Yep.
So 10 customers represent 10 different people coming into the store and being served or greeted first by either Mo, Flo, or Joe.
So the probabilities we get for Joe, Mo, or Flo, 0.35, 4, 0.4, and a quarter, are for each individual person that comes into the store. So you can see each individual person as a trial. So when 10 customers come in, there are 10 trials or experiments.
So 10 customers enter the shop on Monday. Find the probability that Mo is the first to greet exactly 3 of those customers. Exactly. Is that a key word?
It is, Mr. Gibb. Exactly. When we know we have exact probabilities, we know we want to use the formula. Now the formula is...
Whoa, Mr. Rashid. What type of problem is this?
It's a binomial question, sir.
So what's the first thing we need to do? What do we need to tell the examiner?
Oh yeah, that is a binomial question. So we can write this down. So we are talking about Mo. So instead of writing x, I can write m. It's a binomial, so I can b. n, look at the question. There are 10 customers, so n is 10. And the probability for Mo is 0.4, so we've got this down, and we've got a mark there.
Excellent. So I know, and you know, and the examiner knows that you know that that was binomially distributed. Brilliant.
Cool. Now, it's an exact. When you're doing exact probabilities, we want to use the formula. Now, this is the formula. So the formula says the probability that the random variable x is equal to r is n, so that's your sample size, choose r, p, so times p to the power r times 1 minus p to the power n minus r. So in this question, we're working out the probability that m is equal to, well, it says exactly 3, so probability m is equal to 3 is equal to, well, n we've already worked it, we already know where it is 10. Choose 3, and p is 0.4, so times 0.4 to the power r, so r is 3, times 0.6 to the power n minus r, so it's 10 minus 3, which is 7. Now, to work this out, to work something like this out, you use your calculator. So get your calculator up and work this out. So n choose r is this button over here. So we've got 10 choose 3 times 0.4 to the power 3 times 0.6 to the power times 0.6 to the power 7. And that gives us an answer of 0.214990848.
Right, let's get that answer down.
Do I have to, sir?
It's quite a long answer. So why don't we write down the majority of it? Equals 0.2149908 ... Number's too long. 3 significant figures. 1, 2, 3. We're going to cut it off there. The 9 will round the 4, so our answer would be 0.215 to 3 significant figures. Now, a couple of things that are worth pointing out here before we carry on. And let's look at some of the patterns within the question. 3 and 7. There's 3 trials for the first part, 7 trials for the second, and their total equals 10 trials. Secondly, the probabilities. 0.4 was the probability that Mo met the customer first. The probability that Mo did not meet the customer first was 0.6. Reason being, 0.6 plus 0.4 equals 1. Okay, question B. On Tuesday, 15 customers enter the shop. Find the probability that Joe is first to greet no more than 4 customers that day. It's very key information that no more than 4 customers, so I'm going to underline it. Then, we'll acknowledge what we need to know for this question. That first of all, n equals 15. The probability of Joe greeting a customer first is 0.35. So, going back to we need to acknowledge this is a binomial distribution and let the examiner know. So J is binomially distributed, 15 trials, and the probability of it occurring 0.35. Okay, from this situation it says no more than 4, so we're talking about more than one probability. Definitely recommend in this situation you start considering a number line. Now, 4 is the key number that is in place here, so we'll look at the numbers 3 and 5 outside of it. Now the question says no more than 4, so we were looking for 3 will be included and 4 will be included, so the numbers that we're after here. So the probability, essentially when it says no more than 4, is the same as the probability that J is less than or equal to 4. Now, if we consider what we've done just previously by working out exact numbers, that's the same as the probability that J equals 0 plus the probability that J equals 1 all the way up to the probability that J equals 4. That's going to take quite a long time to do.
Is there another way of doing it? So I don't really want to do all that work.
Well, there are some tables, and I was hoping you could maybe show everyone what the tables are.
Yeah, of course I can. So what you can do is instead of doing that, and you would get the correct answer this way, is use the tables you have in the formula booklet. They're called the cumulative binomial distribution function. That's what it would be under. They are cumulative. So to work out the probability that j is less than or equal to 0, less than or equal to 4, first we need to find the right table. Now in this, n is equal to 15. So we need to go to the table where n is 15. So if you look up here, I've got n equals 15. Now, our probability, p, is 0.35. So we want this column over here.
There are a lot of numbers there.
Yeah, there are. So I'd suggest you can just use a ruler and draw your line so you know which one you're using. So you don't accidentally jump to a different probability. Now, we want less than or equal to 4. So you want to find 4 on your table. It's over here. And look across. And so the number we want is 0.3519, and now we also know how to round that to 3 significant figures, so it'll be 0.316 to 3SF.
Okay, on to the third question, question C. The following day, Wednesday, 20 customers enter the shop. Find the probability that Flo is first to greet at least 6 of the customers on Wednesday. This question seems very similar to the last question, but are there any differences?
Well, yeah, first of all, it's Wednesday, so there's a difference there. There are now 20 customers, so my n is going to be different. N is now 20. And my probability is also different. It's Flo, so probability is a quarter, and a quarter is 0.25. So we can write down f. So I'm using is binomial with n equals 20, p equals 0.25.
So the examiner knows that you know it's binomial.
Yep. So we want to find the probability that Flo is first to greet at least 6 of the customers. So again, I would write down the numbers either side of 6. So you've got 5, 6, 7. Of course, these numbers carry on, but we don't need to write all of those down. It's first to greet at least 6 of the customers. So it's going to be 6 or more. So we can write down probability is f is more than or equal to 6. Now, to work this out, you cannot just use your table straight away, because remember, your table is less than or equal to.
All right, so we have to turn these tables, we have to turn it around.
Yeah, you do.
As the sum of the probabilities is 1, the probability that Flo is 6 or more is the same as the probability of 1 minus Flo is 5 or less.
Excellent. And you can see that. You can see that in your numbers that you've written down earlier. So we've got these is what we want. So you've got 5 or less over here, and these must add up to 1. So you can do 1 minus probability Flo is less than or equal to 5. Now to do this, again, now we can look this thing up in our table. So take us through it, Mr. Gibb.
So the probability of Flo was 0. So first of all, check the table before we go any further. 20 trials. The probability of Flo, 0.25. So it's within this line is what we want. Using a rule is very, very useful here. And we want the probability of 5 or less. Here we have, there we go. So we have an answer. 1 subtract 0.6172, which then gives us our answer of
0.3828.
Rounding to 3 significant figures, 0.383 3SF.
Done.
It's good practice to round at the end of the question rather than midway through, because otherwise your final answer will be around, then you'll be rounding your final answer, which has already been rounded in the first place, which lessens the accuracy. So always round at the end of your question.
Question D. That Thursday, 30 customers entered the shop. Find the probability Mo is first to greet at least 4, but less than 10 customers.
So with this question, again, Mo is distributed binomially. We're telling the examiner we know it's binomial distribution. There are 30 customers who enter the shop, so n is 30, and the probability for Mo is 0.4. Now, before we had less than for our first question. Our second question we had more than. Now we're having less than, but more than. It's a combination of them both. So help clarity and help us answer this question, we're just going to write out the numbers. So 4 is the key number in terms of the less than. So numbers either side, 3 and 5. 10 is our second key number, numbers either side, 9 and 11. So let's read this question again. Mo is the first to greet at least 4, so we want 4 to be included. But less than 10, so we do not want 10 to be included. So this is our number, or this is our section of numbers that we have here. So we can write this as a probability that Mo is greater than or equal to 4 and less than or equal to 9. That covers the box of values or the number line of values that we've mentioned already. Now, to work that out, it's the probability that Mo is less than or equal to 9. That would give us the probability of Mo being 0, plus 1, plus 2, plus 3, all the way up to 9. We don't want all of those values, so we need to take some away. The probabilities that we don't want there, this would be the 3, the 2, the 1, the 0. This not included. So we're going to subtract the probability that Mo is less than or equal to 3. Now these values are cumulative and these values can be taken from the table again.
So now, using the table, we want that, again, make sure you got the right table. N is equal to 30. Again, N is equal to 30 over here. Our probability is 0.4 over here. So again, use rulers, highlight this. Now we need the probabilities for less than or equal to 9 and less than or equal to 3. So look at 9. Here's 9. That number is 0.1763 minus probability less than or equal to 3, which is 0.003. And if we do that subtraction, we get 0.176. And we don't need to round that to anything because that's already two free significant figures.
Excellent.
Question E. On a busier Saturday, 50 customers enter the shop. Find the probability Mo or Flo greet less than 24 customers.
Okay, the probability of Mo is 0.4. The probability of Flo is 0.25. Hence, the probability of Mo or Flo is 0.65. That's quite a big probability. We're going to come on to why that is a bit of a concern later, or could be a concern later. Now, next thing we need to do is acknowledge the fact that this is a binomial distribution. You don't do it like that. What you do is like this. You say Mo or Flo, there we go, it's binomially distributed. We have how many trials? 50 trials. And we have a probability of 0.65. Now, we're talking about Mo or Flo greeting less than 24 consumers first, or 24 customers first. So, remember our numbers, we have 24 trials, 23, 25, and the numbers either side of it. We're looking for less than 24, so we're looking to cut it off here. So this is as a probability of Mo or Flo is less than or equal to 23. Now, next step is we go to our tables. We go to our tables and we can see we have the probability of n equals 50. Excellent. And we go along here, we go along the top, and we have, oh no, the highest probability we have is 0.5. Our probability was 0.65. So what we need to do is go back to the question, revisit it, relook at it. So we had a probability of Mo and Flo, or Mo or Flo, being 0.65. What we can just do is spin that on its head, and we're going to talk about the probability of, or look at Mo or Flo not occurring. That would also be binomially distributed, and the number of trials haven't changed. It's still going to be 50 trials. But as the probability of Mo or Flo occurring is 0.65, the probability of Mo or Flo not occurring will be
0.35.
Why?
Because probabilities add up to 1, and Mo or Flo and Mo or Flo not happening are complementary, so they must add up to 1.
Fantastic. So before we put in this next line here, we're going to have a look at the number of trials because that is important for us. So we've said already the binomial distribution with 50 trials. So overall, we know that 50 trials will occur. So 50 trials occur here, and we know that 25 trials occur, or 50 trials occur overall, and 25 trials occur when Mo or flow happens. When Mo or flow does not happen, there must be how many, Mr. Rashid?
For that one, there should be another 25.
25. 25 and 25 gives us 50. Okay, good. Now, if 24 trials occur when Mo or flow, then must be how many trials that don't occur?
26.
24 plus 26, 50. Excellent. Now let's try that again. If 23 trials occur, then it must be, is it 27?
Yep.
Excellent. So we have 27. So at every single occasion, 50, 50, 50 trials occur, and we can work out what some of them are. Now, for our first trials, we're looking at, or Mo or flow occurring, we're looking at 23, less than or equal to 23. Now we're looking at 27, but it's not going to be less than or equal to 27. It's actually going to be greater than or equal to 27, because our numbers here are
25, 26, 27, so they're going up, so it's going to be more than or equal to 27.
That's exactly what I was thinking, Mr. Rashid. Now, normally, we'd just go, because this is a greater than or equal to, it gets a little bit more complicated again. Because it's a greater than or equal to, we can't just go straight to our tables, we need to consider the opposite, only consider what's not happening. So, if we want to find the probability that Mo or flow not occurring, which we know is 0.35, and that occurring greater than or equal to 27 times, that is the same as 1 minus the probability Mo or flow not occurring less than or equal to 26 trials.
Excellent. So am I right in thinking that this 26 came from over here? If it's not more than 27, it must be less than 26.
Absolutely. So this question had 3 layers of complication here. The first one came about the fact that the probability was greater than 0.65, hence we had to use 0.35, a number that is available and is in the tables. We then had to consider the number of trials. Before, or initially, we had less than or equal to 23. However, when we spun it round, it became greater than or equal to 27. Our number line was very, very important and very helpful in terms of guiding us here. Our final part, and this is something that occurred earlier, was the fact that it was greater than or equal to 27. Hence, we need to use the tables and to use the tables effectively, rather than calculate probabilities of 27, 28, 29 that will take forever. We used 1 minus the probability that Mo or flow not occurring was less than or equal to 26. Excellent. We can now take this information to our tables.
So now looking at the table, okay, so n is still 50, and now I know my probability is 0.35, so great, now I can actually work things out. Now what did I have, what number did I have? I had, if I remember correctly, and now when you're doing this you won't have to remember it, it'll still be on your paper. If I remember correctly, it was 26, excellent, I've got excellent memory there, and so,
well done.
Thank you, sir. So I'm working out the 1 minus, so if you remember, alright, let's go back, we were working out. So the number we have here is 0.9955, so let's try and remember that. So in this question, it's 1 minus 0.9955, and that is simply 0.0045. Now you should be able to do this without a calculator. If you can't do it without a calculator, shame on you.
But you do get a calculator.
You do get a calculator and you can get the marks.
Okay, a big, big question there, and probably one of the hardest questions you can expect to see from the binomial. However, if you can manage to get your head around this and practice a few questions like this, then put you in a very, very good position. Okay, Sundays are quieter day. This is our final question, and 15 customers enter the store. Find the probability that either Joe or Mo greets more than 12 customers first.
Okay, so Joe or Mo. So first of all, n is 15. Just read off the question. Joe or Mo. So Joe has a probability of 0.35. Mo is a probability of 0.4. I'm going to add these to get the probability of either Joe or Mo occurring. This gives me 0.75. Now I know, well, before we carry on, I can write this is Joe or Mo is binomial with a n is 15. The probability is 0.75. The probability is 0.75. So I can straight away go, I know 0.75, it's more than...
Alarm bells, alarm bells. This is the same, it's similar to the last question. The probability is greater than 0.5, so we can't use the tables in this format.
Yeah, so straight away I can say Joe, or not Joe or Mo, but it's still binomial, n is still 15.
So the number of trials are the same, but what happens to the probability?
Well, it's 1 minus 0.75, so it'll be 0.25.
Little check, 0.75 plus 0.25 equals 1. Sounds like we're on the right lines.
Excellent. Now, it's less than, or it's more than 12. So I'm going to write my numbers either side of 12. So I've got 12, 11, 13. It's more than 12 first. So it's more than, not more than or equal to. So it's 13 or more. Now for the underneath, so this is Joe. So this is Joe or Mo. Now underneath, I'm going to do Joe, not Joe or Mo. So remember, these have to add up to give you your total. In this case, it's 15, or total n is 15. So this must be a 2, this must be 3, and this must be 4. Now, originally I was working out the probability Joe or Mo is less than, if I look back, I was working out Joe or Mo is more than or equal to 13, and I get that just from my number line. Now, that's equal to the probability Joe or Mo not occurring is, well, this bit is you highlight the same bit. So, Joe or Mo occurring more than 13, more than or equal to 13 is the same as Joe or Mo not occurring less than or equal to 2. And this we can work out because we can just look directly at the table, can't I?
Absolutely, the numbers go in the opposite direction, so before it was greater than or equal to, now it's less than or equal to.
Excellent, so P or n is 15, so find your correct table. N is 15, P is 0.25, it's over here. And I'm working out less than or equal to 2. So this is the number I want. So that's equal to 0.2361. And to three significant figures, this is equal to 0.236 to 3SF. And I am done.
So for this final part of the question, let's look at interpretation. Interpretation is really the area where you're going to get the very, very high marks. Make sure B grade students get up to A and A star. Now for the earlier questions, A to F, the probabilities were constant over a period of 1 week. Why would it be unwise to assume these probabilities remain constant indefinitely, forever? Now what could those ideas be? Let's think about the real life situation. So we're assuming, if these are indefinitely, we would assume that Mo, Flo and Joe not only work in the same store forever, they work the same shifts together and they have the same position. They never get promoted, so they're always on the shop floor. I hope for Mo, Flo and Joe's sake that that's not their only job for the rest of their careers.
We also assume the probability is constant, we also assume the probability remains constant. No, we also assume the probabilities remain constant no matter who came into the store. But in real life, we know that's clearly not true. I know, for example, when I wear a suit, I get greeted more often at stores. Also, I imagine people's looks come into it, their gender. There are loads of factors which could determine the probabilities of Joe, Mo, or Flo greeting them. It's not realistic to assume it's constant for every single trial or for every single person, which is in this case on trial.
Absolutely. Probabilities might also change for returning customers. They may have been served by Joe before and want to be served by Joe again, so they make a direct line, beeline towards them, skewing the probabilities. Likewise, sooner or later there will be a customer who comes in and leaves the store without being greeted by anyone.
Yeah, so there are so many things you can mention. Any one of these things can get you the marks.
Well, I hope you enjoyed our little video session today. There'll be more going up there. Blah, 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 blah.